Okay, so we now want to start looking at how we can write differential operators that are given in terms of Cartesian coordinates like this in other coordinate systems. In particular, we're going to look at polar coordinates. So first of all, we need to even understand what we're asking. So here's the question that I'm going to ask and answer in this video. And then in the notes, well, I don't think I actually do this in the notes. I do something very similar in the notes to what I'm about to do here. But in the notes, I challenge you to then take this and figure out how to write their Laplacian in terms of polar coordinates. And I tell you what the answer is. You know if you're on the right track or not. Okay, so here's what I mean. So let's say, here's the question that we want to ask. Or here's what we want to do. Write the partial differential operator x in polar coordinates. That's not really a question, is it? So let me rephrase this as our goal here. And if we can understand, one, what this goal means, and two, how to do it with the partial x derivative, we can then understand how to do it with the partial y derivative, and then we can understand how to do it to the double partial x derivative and the double partial y derivative, and from that figure out how to get the Laplacian. Okay. There's going to be a lot of tedious calculus and algebra in all of this. That's just something that you have to be okay with. But I'm not going to do a lot of tedious algebra and calculus, because I'm just going to show how to write the partial x derivative in terms of r and theta, and then I'll let you do the rest of it on your own. I highly encourage you to do the rest of it on your own to get an idea about how this change of variables works. So first of all, I just want to understand what we mean by this. What I mean when we say write the partial x derivative in polar coordinates. So I'm just going to very generically let this d be the partial differential operator. So let d be the partial x derivative in polar coordinates. So d is going to be like a sum, or maybe a sum and product, or we don't know what it's going to be, but something involving partial derivatives with respect to r and partial derivatives with respect to theta. And what I mean when I say I want d to be the partial x derivative but in polar coordinates, what I mean particularly is if x is equal to r cosine theta and y is equal to r sine theta. So this is just the standard polar coordinate thing. If x is equal to r cosine theta and y is equal to r sine theta, then what I want to have happen is the x derivative of f of xy is equal to the whatever we're going to come up with, the r theta, the polar coordinate derivative of f of r cosine theta r sine theta. So to be a little more, to use this as an example, maybe to be a little more clear, what I want to do is we start with the function e to the minus x squared plus y squared plus x cubed. If we take the partial derivative of this with respect to x, we're going to get minus 2x e to the minus x squared plus y squared plus 3x squared. And then if we convert this to polar, if we convert this to polar, we're going to get minus 2r cosine theta e to the minus r squared plus 3r squared cosine squared theta. Okay, so if we take this and we do the partial x derivative, this is what we get just by doing calculus things. And then if we convert this to polar coordinates, that is, wherever we see an x, put r cosine theta, or wherever we see a y, put r sine theta, we get this right here. Okay, on the other hand, what I'm saying is if we do the polar coordinate first, if we switch to polar coordinates first, and we get this is e to the minus r squared plus 3x, not plus 3x squared plus r cubed cosine cubed theta. So what I'm saying is if we switch first to polar coordinates and then we do this d, whatever this d is, we haven't figured it out yet, then if we do d, we get down to this same thing here. So that's what I mean by saying that d is equal to the partial x derivative in polar coordinates. We can either take the x derivative and then change to polar coordinates, or change to polar coordinates and then do the d derivative, but we get to the same thing. Some of you might have seen things like this before. We can talk about this in terms of commutative diagrams. Okay. All right, so how can we do this? Well, like I mentioned before, it's just going to be several applications, or actually maybe two applications of the chain rule here. So we've got f of xy. So I'm going to use this as an example, but generically, if we have f of xy, we can write this f of xy is equal to f of r cosine theta r sine theta. Okay, so what we can do now is we can compute the derivative of f with respect to r and with respect to theta. So if I look at the partial derivative of f, and because I don't have a lot of room on the board and these computations get long, I'm typically not going to write the argument simply because I need to conserve space. So the partial derivative of f with respect to r is going to be the derivative of f in the first component. That is, wherever I see an r cosine theta in the difference quotient, wherever I have in this first component, in the difference quotient, I'm just going to add h to the first component here. So in the difference quotient, it'll be f of r cosine theta plus h, comma r sine theta. That's what this first notation here, the one notation means here. It says I'm going to take the derivative in the first component. And then it's going to be times the derivative of the first component with respect to r, which is just going to be cosine theta. And then it's going to be plus the derivative of f in the second component times the derivative of r sine theta with respect to r, which is sine theta. Okay. Now I can do something similar with theta. If I do theta, I'm going to have the partial derivative of f with respect to theta is going to be the derivative of f in the first component times the derivative of r cosine theta with respect to theta. So that's minus r sine theta. And then it's going to be plus the partial derivative of f in the second component times the derivative of r sine theta with respect to theta, which is r cosine theta. Okay, so now what I want to do here, so I need to make this observation. Go back to that first notation video that we looked at. The partial derivative, the d sub 1 of xy is equal to d sub x of xy. It means take the derivative in the first component. And now here I'm going to use this sort of ambiguity in notation to my advantage to realize that the partial derivative of f with respect to x, when f is written like this, is the same as the one derivative of f. That is, taking the derivative in the first component. So in other words, I have two equations here. What I want to solve for is this partial sub 1 of f. That partial sub 1 of f is the partial derivative in the x variable. That's what that means. Because again, it means wherever I see the first component, I'm going to add plus h. Okay, but if I have f of xy, this means wherever I see an x, I'm going to add a plus h. So this notation means in the first component, I'm going to add a plus h. This means wherever I see an x, I'm going to add a plus h. But this, because x is only in the first component, and it shows up just as x and not like 5x or x plus 5 or something like that, these are going to be the same thing. So my goal here is I want to solve for the partial one derivative of f. This is I now want to think about this as an algebra problem. I've got a system of equations here. My unknowns are the partial derivative, the partial 1 derivative, and the partial 2 derivative. My goal right now, because that's what I'm asking, is to solve for the partial 1 derivative. I could also ask the same question and solve, if it was a partial y here, I'd be finding the partial 2 derivative. Okay, so there's however you want to solve systems of equations, you solve it that way. I'm going to maybe take advantage of some of the trigonometry here, and I'm going to multiply the top equation by r cosine theta. So I'm going to multiply the top equation by r cosine theta. I'm going to multiply the bottom equation by sine theta, and then I'm subtracting them. So it's going to be minus partial theta, minus sine theta partial theta f. Okay, and again, this is going to get long, so I'm going to come down here on a new line to write what it's equal to. Okay, so when I do this, for the first thing, I'm going to get the partial 1 derivative times r cosine squared theta. Okay, then it's going to be plus the partial 2 derivative times, I'm multiplying it by r cosine theta, so it's going to be r cosine theta sine theta, and then minus, okay, I'm multiplying the bottom one by sine theta, so it's minus, well, it's minus a minus, because there's a minus sign there, so it's going to be plus the partial 1 derivative of f times r. Well, if I multiply it by sine, it's going to be sine squared theta. And don't forget we're subtracting, so for this next term, it's going to be minus the 2 derivative of f times r cosine theta sine theta. Well, these two terms cancel out. If you look at here, there's a common on these two terms, there's a common factor of the 1 derivative of f times r. Cosine squared plus sine squared is equal to 1. And so what we find is that this is equal to r times the first derivative, times the derivative in the first component, which, again, based on this over here is what we wanted to look at. Okay, so now the answer to the question over here is that in polar coordinates, the partial x derivative is equal to, if I divide both sides of this equation by r, you get cosine theta times the r derivative of f minus 1 over r times sine theta times the theta derivative of f. Okay, and again, just to illustrate what I mean by this, I'm going to go back to this example. All right, so I'm going to start with f of xy here. And I'm going to take the x derivative in just Cartesian coordinates. And when I do that, I get minus 2x e to the minus x squared plus y squared plus 3x squared. And then if I convert to polar, I get minus 2r cosine theta e to the minus r squared plus 3r squared cosine squared theta. Okay. Now, on the other hand, I can begin by converting to polar coordinates. If I convert to polar coordinates, I get e to the minus r squared plus r cubed cosine cubed theta. And now what I could do next is apply my differential operator. I'm going to call this, I'm just going to keep calling it d so I can have better notation here. I'm going to apply my differential operator. So what I'm going to get is going to be cosine theta times the partial derivative of this with respect to r. So it's going to be cosine theta times the partial derivative of this with respect to r. So it's minus 2r e to the minus r squared plus 3r squared cosine cubed theta, and then minus 1 over r times sine theta. Let me write this as sine theta over r times the partial derivative of this with respect to theta. Okay, so I'm going to do the derivative. The derivative of that with respect to theta is 0. So I just have this part right here, and that's going to be 3r cubed cosine squared theta, but then times the derivative of sine theta, or sorry, times the derivative of cosine theta, which is minus sine theta. Okay, so this minus sign is going to be multiplied to get a plus sign. Okay, so now I'm going to do some rearrangements here. So by the way, just to get some an idea on how I think internally here, I always get nervous at this part because there's so many different ways I could have made a mistake. I know this is the right thing here, and this all looks familiar to me, but I get so nervous every time I do this because if it's wrong, then I have to go back and basically make the entire video over again, or maybe just this last part here. But everything looks right here. I think everything is going to cancel nicely to give us this. Okay, so now what we're going to look at is, if I look at this first piece right here, I'm going to get minus 2r cosine theta e to the minus r squared. Okay, that matches up with exactly what we have here. Okay, then I'm going to have plus, here's the nervous part, 3r squared cosine to the power of 4 theta. When I just distribute the cosine over there. And then if I do r cubed over r, that gives me r squared. And so what I get when I do that, I'm going to have plus 3 r squared. If I distribute the sign over there, it's going to be times cosine squared theta sine squared theta. I think that's still viewable. Yes, I think the whole board is viewable. Okay, and now what we get, and look at how well this is going to line up for us. This will be minus 2r cosine e to the minus, cosine theta minus 2r cosine theta e to the minus r squared plus, okay, what's going to happen over here? Well, notice there's a 3r squared in both terms. What else is there in both terms? There's a cosine squared in both terms. There's a cosine squared there and a cosine squared there. So this is going to be 3r squared cosine squared theta. And then what do we have left over from this term? It's a cosine squared, and from this term is a sine squared. Cosine squared plus sine squared is 1. So this is what we have. And in fact, these two things are equal to each other. So these two things are equal to each other. This equal sign means this, but you know, providentially, it looks, you know, it lines up here as well, which is exactly what we wanted to show. And again, so what we've done here is in the black ink over here, we've done f of x. We've taken the x derivative, just using normal calculus rules of x derivatives, and then converted to polar coordinates. This is what we have. Over here, what we've done, we have gone from f of xy to polar coordinate first, and then using this d operator, this differential operator, which is the x derivative written in polar notation, we've done this, we've taken the derivative here, and they are equal to each other. And so again, this is just what it means when we say write the partial x derivative in polar coordinates. It means find the thing that does this. And I showed you the procedure for how to do this. In the notes, I also show you the procedure. I also explicitly sort of show you the procedure and show you what the partial derivative is with respect to y. Now, what I ask you to do in the notes is to then find, and what I use later in the notes, is to then find the Laplacian in terms of polar coordinates. So this is going to involve two things, well, several things really. We need to next figure out what the double x derivative is. Okay, we need to next figure out what the double x derivative. So this is the x derivative. We now, if I have, I now need to, so something very similar, and I need to figure out what the x derivative is. Now the x derivative is going to be in terms of the double derivatives of r and theta. The double x derivative and the double y derivative will be in terms of r and theta. So what you have to do next is you have to figure out, so you remember, to figure out the double x derivative, we computed the double r derivative and the double theta derivative. So you have those two equations, or those two expressions. What you need to do next is compute the double r derivative and the double theta derivative, and the r theta derivative as well, probably. And then from those, figure out how you can figure out the double x derivative plus the double y derivative. It's complicated, and like I said, there's going to be a lot of tedious algebra to do, but it is just tedious algebra. You're going to have enough equations that relate all of these things that you're going to be able to figure out what to do. So again, when you do what I said, when you compute, let's say, the double r derivative and the double theta derivative, maybe start there. Maybe you'll see, okay, I have my double x derivative here, my double y derivative, and those are like my unknown variables, and I can solve for those to figure out what the Laplacian is. Okay. Anyways, you guys definitely can do it. No doubt in my mind that you can do it. It's a good exercise. Everybody should do it once in their life. I highly encourage you to do it. I'm just going to tell you what the answer is, so I can use it. But that's it for this video.